Okay, so the final video for kinetics is about catalysis, about catalysts and how they work. Hey, you may be familiar from biology with the definition of this definition of a catalyst. A catalyst increases the reaction rate without being used up in a reaction. So, how does this happen? Well, now that we've studied kinetics, we can explain why this is true. There are actually a couple of things going on. One thing that happens is a catalyst changes the mechanism. So the mechanism has a different number of steps maybe, or different types of collisions, or something that changes the mechanism of the reaction. Okay. The other thing that happens when we change the mechanism, that new mechanism has a lower activation energy. So that's the other key. So a catalyst increases the rate of reaction by lowering the activation energy through a change in mechanism. So the other thing we'll notice is that catalysts, we start with a catalyst. Many times the catalyst is consumed in one step and then regenerated. So it's kind of the opposite of a reaction intermediate. I start with some, I use it up in one step, but get it back in a later step. So if we're looking at activation energy diagrams, the red curve indicates the uncatalyzed reaction. So here is the uncatalyzed reaction. It has a relatively high activation energy. Down here, you'll notice the catalyzed reaction. One, it has a lower activation energy, but two, it has a different mechanism because now this catalyzed reaction is happening in two steps, where the overall reaction is only happening in one step because I have one activation energy hill here, there are two here. The activation energy of the catalyzed reaction is still at that slow step. This would be the rate determining step for this reaction, but you'll notice its activation energy is lower than the activation energy of the uncatalyzed reaction. And that's how catalysts affect the overall speed of a reaction, by lowering that barrier for reactants to become products. So there are several different types of catalysts. One is called a homogeneous catalyst. So again, we have two different reactions. The red line represents uncatalyzed, blue represents catalyzed. In my uncatalyzed reaction, I have two gases, O3, ozone, and oxygen atoms. And they are reacting to form two oxygen molecules. In the catalyzed reaction, what you'll notice is that we have three things. Not only do we have an oxygen atom, but we have a chlorine atom in the same state as the other two. That's where the term homogeneous comes from. So all three of these things are in the same state, and this chlorine atom changes the mechanism, lowers the activation energy, but you'll notice I get the chlorine back. So probably what is happening is the chlorine is used up in this step and then regenerated in this step. That would be a homogeneous catalyst. And a heterogeneous catalyst, this is where we a lot of times use metals such as nickel or platinum to catalyze a reaction. This is illustrating the a hydrogenation reaction, where we're adding hydrogens to a fat. So here is my liquid fat, and this fat is unsaturated. This is an unsaturated fat because it has a double bond. Unsaturated simply means if I have a double bond, if I break that double bond, I can add more hydrogen. So think of unsaturated as not having the maximum amount of H's attached to a carbon possible. So what happens when I want to saturate this with hydrogens, when the hydrogen gas is added to this unsaturated fat, in the presence of nickel, what happens is the hydrogen molecules, as they approach the surface, break apart into hydrogen atoms. And the nickel surface holds each of those hydrogen atoms in place, and then the unsaturated fat comes down and this double bond hits this double bond, breaks, so now I have a single bond here, and now I have these two carbons are also attached to the nickel. Once that happens, then the hydrogens attach to the carbon and take the place of that second bond in there, and then I get a saturated fat. So this is a heterogeneous catalyst because I have hydrogen gas and this fat, which would be in one state, and then I have this solid nickel catalyst, which is not really being used up for the reaction. It's simply a place for the reaction to occur. So by having the nickel here, it facilitates that double bond breaking and two hydrogens attaching to the double bond to become a saturated fat. The third type of catalyst is an enzyme. Okay. You probably remember this from biology. Enzymes are locks and keys where the substrates fit into the enzyme, and then the reaction takes place once the substrate locks into the enzyme. So what the enzyme really does, this whole idea of lock and key, of the substrate fitting into the enzyme, is that the enzyme orients the molecule in such a way that it makes the reaction occur more quickly. So this substrate, in this case decomposing all by itself, probably has a very high activation energy because it just has to be positioned just right, or it has to twist just right in order for the molecule to break apart. But what the enzyme does is when that substrate attaches, it twists the molecule around and causes it to be easier to break the substrate apart and then to form products. So enzymes are really orientation tools. They properly orient a single molecule or multiple molecules so that the orientation is all set up for an effective collision to occur.